Hello and welcome to my talk on the Guardian Council, our new parallel architecture to provide security analysis and debug sanitization at very low overheads. We achieve this using tiny parallel compute units, which we call Guardian processing elements, attached to each conventional CPU core, of which they can observe all of the instructions to work out what the CPU is doing and whether the application it's running at the moment is being attacked. So there are lots of different attacks that we need to protect against nowadays. We have on the screen to the left of me things like traditional programming errors like buffer overflows and use after freeze that we want to protect against very efficiently. Things like malware analysis, which you can do offline very cheaply or with coarse-grained analysis very cheaply. But if you want something more complex, then it quickly becomes too expensive in software. Things like Spectrum Meltdown as well, where it's your microarchitecture that's being attacked using its own speculative execution. Things like Rowhammer, where it's a DRAM hardware bug. You may need to protect against any of these different attacks at the same time, and we're going to show you how, with the Guardian Council, you can protect against attacks on a variety of different parts of the system with very low overheads using our new parallel framework. Traditionally, you've got sort of two approaches for security defenses. One of them is doing it all in software, which is very flexible. You can write anything you like in software. You can change it all at a later date. But you don't tend to get very good visibility. You can't see what other processors are doing if the analysis is in your process. You get very high overhead because you have to, for example, instrument all of your code. And you don't get very good guarantees because you can't actually look at that much of the execution in the low sort of 5% overheads that you need for real-world deployment. If you look at hardware, then of course you can make things far more efficient by having very custom logic to avoid taking away from your main programmable CPU's resources. But on the flip side, hardware design is very slow to react. You have a typical period of about 2 years before an accelerator makes it to market. By that time, the attacks might have changed completely, or your hardware might have been circumvented and be useless. However, hardware does give you better visibility because you can see everything that's happening in your system, and thus you can get a lot stronger guarantees by running more intensive analysis tasks in your custom units. Well, what we want to provide then is a third way, where you can get the flexibility of software, but the high performance, low energy consumption of hardware. To do this, we need our system to give us three things. We need it to protect against current and future threats, not just the attacks of today, but be programmable enough for the attacks of tomorrow. We need to be able to emulate all of those techniques currently running in software or currently running on hardware, because really we want to replace those with a generic programmable framework that can do the lot. And of course, we need low area, power and performance overheads because everything does. It's very rare for people to be willing to pay more than about 5% for security in practice. People just turn things off if you can't get those very low overheads. So, our approach to solving these problems is our new architecture, the Guardian Council. What we have over to the left of me is a regular out-of-order superscalar CPU on top for user programs connected to its traditional cache framework. The things that we actually change are all of the things on the diagram to the bottom. The first thing we add then is this event filter, which tracks all of the committed instructions of your main programmable CPU and checks whether any of the Guardian kernels, which are programs that we will be running for security analysis on the little cores at the bottom, whether any of these little cores will be interested in that particular instruction at the moment. If they are, then we send this through to the mapper, which chooses which of our many little programmable units we're going to send this event to. We have lots of these programmable units, these Guardian processing elements, which can all run different analyses at the same time, or perhaps different threads of the same analysis if that analysis is parallel. In detail, these Guardian processing elements are tiny two-stage CPU pipeline cores. They have a fetch and pre-decode stage and a decode and execute stage. These tiny CPUs can be run at about a gigahertz, but they're very, very low power, very tiny. We have a traditional cache setup over on the left there to give them shared memory access, which goes through to the shared L2 cache with the main core. And over on the right, we have something that looks more akin to message passing. We allow these little GPE cores to pass messages to and from each other, so that they can communicate more directly. And we also allow them to observe the main core's operations by allowing the mapper to send messages to these GPEs via the main core, via the filter, via the mapper, then through to the appropriate core via these FIFO queues over on the right. The whole reason this technique works, the trick behind the Guardian Council, is that a traditional big core, even a small big core like the Cortex A57, is about 1,000 times bigger and 1,000 times less energy efficient than the tiny microcontroller-sized cores that we use for our Guardian processing elements. So, if you have thread-level parallelism in your workload, which we're going to argue that you typically do for security analysis, then you can get lots and lots of these tiny little cores in a very, very small fraction of the area and power overhead of your main CPU, and do a lot of analysis of the computation of that main CPU without really paying very much of a cost for that. So, the way we get out this parallelism is that we run lots of different analysis tasks at the same time. For example, your side channel analysis can be running on one Guardian processing element at the same time as your malware analysis is running on a different one. That's one form of parallelism in terms of task level parallelism, but in general you will also have parallelism within a task. You can spread a task that is more complicated, needs more compute power than a single Guardian processing element will provide. You can spread that across multiple different GPEs using thread-level parallelism within the analysis task. Now we're going to look at an example of just how you can parallelize these workloads. We have more examples in the paper, but the one we're going to focus on here is a shadow stack technique. What we're trying to do here is analyze our return stack to check whether anyone is trying to do a return-oriented programming attack on us, for example. In this example, we split the analysis over 5 different Guardian processing elements. The first 4 take in observations, filtering out any call and return pairs to the same location. We know that call and returns to the same location match, so we can get rid of those. It's the other ones that we're more interested in for attacks. We switch between different Guardian processing elements whenever one of them's queue is full, and therefore a single Guardian processing element doesn't have enough performance to cope with the entire analysis. For example, over on the left here, in the blue box at the top, we've got a call X, a return X, a call Y, and a return Y. Those both match, so we know there's no attack there. But there will be some push-pop pairs between different GPEs where we don't know at this stage. For example, we have the call X in the blue box that will be matched later by one of the other GPEs. We don't know yet whether this is an attack. So we have to send it for further analysis over on the right-hand side. We group together any that we don't have the matching pair for and check it over there to get a global view of what the application is doing. And in this case, we see that actually we don't have correspondence. We have a call X and a return Q. There is a non-matching element in this sequence. There's an error, we've been attacked, and so we need to report this to the system. So That's a way of getting out parallelism from this workload in the Guardian Council framework. And in fact, the overheads of our hardware setup in general are much lower than they are in traditional CPU software-based frameworks. We have a series of things in this comparison graph, different control flow integrity techniques, the shadow stack technique we just talked about, a sanitizing technique based on address sanitizer, which is used to check for buffer overflows, for example. You still pay some overhead with the Guardian Council in terms of performance, because you potentially use some of the main system's memory bandwidth, and potentially a Guardian kernel has to pause the main CPU very briefly because it doesn't have enough compute resources to deal with the throughput of events coming through from that main core. But the overheads are a lot lower than they are in software, which means you can add a lot more of this analysis within the 5% budget that is typical for what people are willing to pay. In more detail here, we see some of the highlights from the overhead of the shadow stack technique. The full results are in the paper. This is just the interesting subset of Spec 2006 for this task. We see that for that shadow stack example we saw a moment ago, there are some workloads where actually 2 GPEs, 1 filter and the tiebreaker that was originally over on the right, are nowhere near enough performance to avoid slowing down the main core significantly and achieve reasonable overheads, because the single-threaded performance of our Guardian processing elements is so small. We see that over on the left for Omnet PP, we get a 6x slowdown. However, by adding more and more GPEs, by exploiting more and more parallelism, we overcome that single-threaded limit, and thus you reduce the overheads well down to 5% on average by 8 Guardian processing elements. If we look at the sanitizer technique, then the parallelism becomes even more necessary to exploit. The single-threaded performance of a single Guardian processing element over on the left causes as much as a 30x slowdown, because you really are doing a lot of security compute at that point. You can't even hope to keep up with the main core, but by the time we use 24 Guardian processing elements, still very small in terms of area and power overhead, the overheads have become vastly diminished because this is a very parallel analysis. One of the more interesting things about the overhead of the Guardian Council is that the overheads of different tasks tend to combine not as a multiplication, but as a maximum. A 5% overhead from one and a 5% overhead of the other tends to give us a 5% overhead rather than a 10% overhead. This is because when a Guardian kernel does cause slowdowns, it causes the main core to slow down and therefore generate fewer events. Therefore, the other Guardian kernels have less work to do. Therefore, you can run lots of Guardian kernels at the same time without causing lots and lots of overhead from their combination. Another interesting property that the Guardian Council has is that it's decoupled from the main core. You potentially have to wait a few cycles to get the results back. We have mitigation strategies for how this affects security in the paper, but you also get fairly interesting observations from the amount of time it takes to detect an error on the Guardian Council. Here we see a setup for Rowhammer prevention, deliberately given fewer Guardian processing elements than it actually needs so that we do get some slowdown. And we see that on the left-hand side, there's a very bimodal output in terms of the delay between the event happening on the main core and being analyzed by a Guardian kernel. On the left, we have delays where it's just a few cycles, it happens straight away, whereas over on the right, we have delays that are more in the 400 nanoseconds range. This is because on the left, the Guardian processing elements FIFO queues are effectively empty, so that means the analysis happens straight away, whereas over on the right, because the Guardian kernels are Guardian compute element compute bound, they don't have enough compute to do the analysis. We have to fill up our FIFOs, and therefore we have to wait for everything else to be processed before the current element is processed. However, if we look at the shadow stack example, you get a very different pattern. You get this very distinct box shape appearing. This is caused by the method of parallelization that we use here. We match calls and returns together on one Guardian processing element until its FIFO is full, then we switch to a different FIFO element. That means that we're basically always generating this waiting behavior in the FIFO queues, which means that we can have quite a big delay in waiting for our filtering to happen before the event is actually processed. So that's a very brief introduction to the Guardian Council. We cover a lot of these very high-level concepts in far more detail in the paper, so please take a look at that if you're interested. We also have a data repository and GitHub where you can check out the code. You can see examples of lots of different Guardian kernels and potentially write your own. You can run them all using scripts on our Gem 5 based simulator. Please ask questions either in the comments thread below or on the ASPLOS Slack channel. Thank you very much for listening, and I hope this was interesting and informative.